Assalamu alaikum dear students, how are you? Today we are going to discuss law of mass section. Law of mass section was presented in 1869 by Guldberg and Waage. They were the Norwegian scientist. Guldberg was a mathematician and Waage was a chemist, and they were relative to each other. This law is based on the relationship between rate of a reaction and the active mass of reacting substances. It is said that if active mass of reacting substances is more, it is a higher value, then the rate of reaction will be also very high, and reaction will proceed in a very speedy way. And similarly, if the active mass of the reactants or products are less and low in value, it means the reaction will proceed very slowly. So it tells about the relationship between the active masses of substances and their rate of reactions. Now we will discuss first of all the definition of this law. This law states that the rate at which a substance reacts is directly proportional to its active mass, and the rate of a reaction is directly proportional to the product of the active masses. This law is in fact divided into two smaller parts. One part describes that if the reacting substance is only a one thing, it is only a one substance, then its rate of reaction will depend on its active mass. And the second part of this law is if the reacting substances are more than two in number, or two or more than two in numbers, then the rate of reaction will depend on the product of their active masses. The more the active masses, more will be the rate of reaction, and if the less are the active masses, then the slower will be the rate of reaction. Let's explain it with an example. First of all, we should have a concept about the active mass. Active mass, the mass of substance taken in mole per decimeter cube. If we take the mass in mole per decimeter cube, then its mass will be a active mass. In fact, active mass is a ratio between number of moles and a volume of the reacting substances. Number of moles and over the volume, the unit of volume is a decimeter cube. So the active mass is expressed in mole per decimeter cube, and it is represented in square brackets. Let's have a reaction. Reaction is A reacts with a B in a reversible reaction to form C and D. Here we will express, first of all, we will express the active masses of these reacting substances. A active mass will be A square bracket, B active mass will be B square bracket, C active mass will be C square bracket, and D active mass will be D square brackets. First of all, in a reaction between A and B that goes into C and D, we will focus on the rate of forward reaction. Rate of forward reaction, dear student, is directly proportional to the product of A and B. And rate of forward reaction, we will replace the proportional sign with equal, and we will put a constant here that will be Kf into A and B. The rate of reaction will be equal to Kf into A into B. Now we can write the rate of reverse reaction, and rate of reverse reaction will be directly proportional to the product of C and D, as the C and D are taking part in a reverse reaction to produce A and B. So a rate of reverse reaction will be equal to Kr into C into D. Now at equilibrium stage, what happens? RF, rate of forward reaction, becomes equal to the rate of reverse reaction. As we know, rate of forward reaction is equal to Kf into A into B, and is equal to Kr into C into D. Now we will take a constant on one side and the reactant product on other side. Kf will be divided by the Kr. Similarly, C and D will be divided by A and B. Then Kf will be equal, Kf will be divided by Kr. As we know, Kf over Kr gives another constant, that is a Kc known as a equilibrium constant. Now we can write this expression as Kc is equal to C into D over A into B. Here Kc is a equilibrium constant. This law is explained by an example. Now we can explain this law with the help of a general reaction. And in a general reaction, we will put our coefficients in front of each reactant and a product. Like A reacts with a B to form C and D. A will have a small a as a coefficient, B will have a small b as a coefficient, C will have a small c as a coefficient, and D will have a small d as a coefficient. Remember, these coefficients represent the number of moles as in a balanced chemical equation. Usually we know we put 2, 3 or 4 before our reactants or products when we balance a chemical equation, and that number is known as a coefficient, and this coefficient is represented by a small a, small b, small c and a small d. Now in this reaction, the forward reaction can be explained as A will react with the B to form C and D. The rate of forward reaction here will be directly proportional to the A into B, and their coefficient will be their powers. A will have a small a as a power and B will have a small b as its power. Now coefficient will be replaced by Rf will be equal to proportional sign will be replaced by a constant that will be Kf into A small a into B small b. Rate of reverse reaction similarly can be written as C when react with a D to form A and B. Here capital C will have a small c as a coefficient and capital D will have a small d as a coefficient, and capital A will have a small a as a coefficient and capital B will have a small b as a coefficient. Rate of reverse reaction can be written as rate of reverse reaction is directly proportional to the C into D raised to their power small c and a small d. Now rate of reverse reaction will be equal to Kr, that is a reverse reaction constant, into C into D, dear student. Now we can write at equilibrium condition rate of forward reaction becomes equal to the rate of reverse reaction. Rate of forward reaction, as we know, is equal to Kf into A into B, and their powers are small a and small b is equal to Kr into C into D raised to their powers small c and small d. Now we can write the constants on one side and reactants and products on another side. Kf over Kr will be equal to C D small c and small d as their coefficient. Similarly, capital A, capital B, small a, small b as their coefficient. As we know, Kf over Kr are the equal to another constant, that is a Kc. Kf over Kr equal to another constant, that is Kc. Now the Kc will be equal to capital C, capital D raised to their power small c, small d over capital A, capital B raised to their power small a and small b. This is the final expression of a law of mass action for a general chemical reaction, and this was the expression of a law of mass action of a example. Now we can conclude our lecture seeing that rate of reaction usually are directed proportional to their active masses, and if a reactant have a higher active mass, it will have a high rate of reaction, and if a reactants or a product have a lower masses, their rate of reaction will be also in a slower side. The expressions we have derived with the help of an example and with the help of a general chemical reaction. Kc was the final expression, and Kc is known as a equilibrium constant, that was equal to as I mentioned, that is equal to the ratio between product of the products raised to power their coefficient over product of the reactants raised to power their coefficients. So now we can conclude that the Kc is the equilibrium constant in the law of mass action. In the next video, inshallah, we will going to discuss about the Kc in a detail and its unit, and the effect of Kc on the rate of reaction, direction of reaction, and on the extent of reaction. Inshallah, we will discuss in upcoming videos. Till then, Allah Hafiz and take care.